Welcome back, fellow colleagues. This is 190 reverse bits. Not gonna lie, this problem's kind of difficult. It's marked as easy, but if you're not familiar with bit shifting operations, it's a little bit confusing, not going to lie. But this is going to look at a very simple solution, introduce some very simple bit manipulation operations, and then we'll work through the problem. Right, so before we even talk about, the problem says reverse bits of a given 32 bits unsigned integer, right? And so basically what they're asking is numbers represent, let's just assume that we're working with numbers represented using 4 bits, right? So what we get there, unsigned, right, are 16 possible different values, so pretty much 0 to 15. To pass in 15, right? 15 in binary is going to be one. Okay, that's a bad example. We're going to do 14. So it's going to be like this, right? So 14 passed in, reversed as binary, right, is going to be 0, 1, 1, right? And that, reversed as binary, is going to be, well, 1 plus 2 plus 4 is 7, right? So 1 plus 2 is 3 plus 4 equals 7. So what you want to pay attention to, right, the decimal numbers here don't really matter, right? So you don't want to get caught in thinking about these decimal numbers, right? You really want to get caught in thinking about these binary numbers here, right? And so what's important to note, right, is that how do we go about reversing these bits, right? So under the hood, right, 14 is represented using, in this problem, you're assuming 32 bits, right? 14 is going to be represented with 32 bits, right? But you can pretty much imagine this, right, with 32, well, 28 other zeros in front of it, right? And so if that's the case, how would you go about reversing it, right? Well, wouldn't it be as simple as just, if we started over with 0, right? Wouldn't it just be as simple as saying, hey, what's the last bit? What's the rightmost bit of the input number? Oh, it's 0. Okay, well, let's go to the next one, right? What's the second rightmost digit, right? 1. Right? Okay, now what's the third rightmost digit? 1. Now what's the fourth rightmost digit? 1, right? And then you get the same answer we got before, right? Which was 7. Right? So basically what you find out is that just taking the last bit of the input number, right, and then putting it, right, at the rightmost end of the output number, right, you will get the reversed bit, right? So how do we do this with bits, right? So what we did before, we just looked at the rightmost bit, and then we put it on the other output number, on the other output variable, right? And then we just kept doing that until we did it, right? So how would you do this with bit operations? So up here I have a very simple example, right? So here are some bit shifting operations. So we have 0, 1, 1 here, right? 1, 2, 4, 8. So this is 6, right? If you shift this over 1 bit to the right, so you can see these arrows are pointing right, this is a right shift, right? These bits, you can just slide these numbers over 1 bit, right? And the vacant space, right, is filled in with a 0. So you can see that here. We slid all the numbers, right, over 1 position, and then a spot opened up here, and we just fill that with zeros. Same thing with a left shift, right? So we want to slide all the numbers over here 1 position to the left, right? We do that, we create an open position at the end, we add a 0, right? So with this, we can see that if we want to get the rightmost digit of, well, if we want to, I guess, right, slowly slide, in a way like iterate, but not really. If you wanted to move this digit downwards, right, and slowly kind of be able to access the rightmost digit, you could do that, right? So couldn't you just say, if you wanted to get 0, right, you could just say bit shift 1, right? And what you would see, right, is that this would become like this, right? And then if you shifted it again, right, you would get this, right? And then if you did it again, you would get this, right? And so you would just kind of keep going, right? And at each point here, we can see that that this is, if we do it one more time, we'll see that we get 0, right? And what the key is here, right, is that we can kind of push the positions down one at a time, right, if we shift the number, right? All right, so I'm kind of hinting that we're going to be shifting our input number down 1 bit each time, right? So now that we can do that, right, how do we get that last bit, right? So we can say, right, we can say, hey, we can actually AND it, right, with 1, right? And this is kind of a mask is what is happening here, because 1 is represented by the rightmost bit, right? And so we're saying if n's rightmost bit and 1, we're saying is if n's rightmost bit is 1 and 1, right, then that's going to return 1, right? And so that's how you can kind of copy bits. But if you said if n is this, right, and we say, hey, n and 1, right, it's going to return 0, right, because 0 and 1 is not 0. 0 and 1 is 0, right? And so we wouldn't add anything there, right? And so with that, if that was the case, right, if let's just say we started our output with 0, we said, hey, is the rightmost bit 1 right now? It's not. Well, it's 0. So we're like, oh, okay, that's cool, right? And then we can continue to build this with a very simple set of operations, and we'll say, hey, it's 0. I guess that's okay. So we're just going to shift the output to the left 1. And so we get 0, 0. And then we're going to say, hey, we have to shift the input over 1 bit as well. So now this is going to look like this, right? And then we're going to say, hey, is the rightmost bit of the input 1? And we're going to say, yes, it is, right? And then we're going to change this to 1, right? And then we're going to we're going to left shift our output again, and we're going to get 0, 1, 0. And we just keep doing this over and over. And what you get is that eventually, if you keep doing it over and over, that we'll have reversed the bits perfectly, right? So what does this look like, right? So we're going to have an output variable. We're going to start it at 0, right? And the problem says that we're going to give it a 32-bit integer, right? And what's important to note there, right, is that no matter the input, no matter the decimal number that gets passed in here, right, it's going to be within the bounds of 32-bit number, right? Which means that at the base case, this algorithm is always going to do 32 iterations, right? Because the number that has been given to us, right, is a 32-bit number. And so I put n there, that's my bad. I'm going to put 32. So basically we're always going to do 32 operations, right? And you can see that's in our input, right? So they give us a number, right, which is really a decimal number, right? But they're representing it here as a binary number with 32 bits, and then it gets reversed and it produces a different binary number, right? So what's the first thing we have to do, right? Well, the first thing we have to do is we have to shift our output, right, 1 bit to the left, and we'll say output. We're just going to shift it 1 bit to the left, right, just to get started and throw a 0 in there, right? From there, we're going to say, hey, is the rightmost bit of n1? If it is, because this is another way of saying if the rightmost bit of n is 1, right, we're going to say output plus equal 1, right? And then since if it was a 1, we copied it over, right? And if it was 0, we didn't copy it over, right? So we're just going to shift we're going to shift the input now, right? Oops, not input, it's n. We're going to shift n over 1 bit, right? And this is the whole brunt of the algorithm right here. If we click submit, expected unindented block, output equals 0. Oh, okay, my bad. I didn't realize we have to shift everything up. And if we see that, we submit it, right, and we get the answer. So what space does this run in? I mean, what's the time complexity here, right? The time complexity here is actually going to be constant time. Well, why is that, right? Well, they said, oh wait, actually, what's going on here? First time doing this problem, by the way, actually true. But what we can see is that they said for given a 32-bit integer, right? So this iteration, regardless of the number that's passed in, it's going to be within the bounds of 32 bits. So we're always going to do 32 operations. So this algorithm runs in constant time in the sense that it's always going to take us 32 operations to complete it. Space complexity, we're only using one variable here. So this is clearly constant space, right? And so the tough part here is just kind of understanding this kind of weird way we're kind of using bit shifting to reverse the bits. There's much faster ways to do this, as you'll see in the solutions tab, but I think it's a great problem that introduces bit shifting in operations. Pogger's champion. So this is 190 reverse bits.